Good morning, friends. I am here with you again for my course, Aircraft Stability and Control. Today, I am in lecture number 63, which is the questions and answers of our module 3. And this module 3 is equations of motion. You know, I am Dr. Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. Today I am going to discuss about equations of motions and in this related topics and why we have to study the equations of motion. So, in this first I will start with Man Ki Baat. Man Ki Baat. Okay. So then after I will go for some axis system, different axis systems and related issues with the equations of motions. Here I am going to tell about my Man Ki Baat. In this Man Ki Baat, till now we have completed the aircraft static stability. When we talk about aircraft static stability, we have done the first one is longitudinal static stability. And then we have seen the lateral and directional static stability. This we have completed. We know that all the systems which really worked, especially the aircraft, the flying of the aircraft is not the static, it is a very complex dynamic system. So, till now we have seen that if we take the spring mass system, this is here spring and here is a mass, this is M, this is the K, and if we disturb by some force, it will start oscillating like this, and if it is in the vacuum, this box if we make in vacuum, this is the vacuum. Okay, in this vacuum, if you give oscillation, it will continue oscillating. It will not stop. So here this, if you take this mx double dot plus cx dot plus kx function of t. Okay, so here we see that in this type of system, and this represent here static case, static system. But if we put some here liquid or some oil in this system or air also, but air is the density of air is very less, this act as a damper. So here in this equation damper is C, and this K is spring constant, and in the static case we only consider Kx. But in dynamic case we have to, this damping also has to be included. We can see here that for forces and moment, if you see forces and moments. So if you take the coefficient of lift CL, this CL is a function of alpha and delta E, but now in dynamic case it is also the function of alpha dot, and it is a alpha dot is rate of change of this angle of attack, and Q is a pitch rate. So in dynamic case we have to take this also, and for very high maneuver this delta E will also have the delta E dot. But here we are not considering, we are only considering this 1, 2 and 3. So if we want this thing, Cl is equal to Cl naught plus Cl alpha into alpha plus Cl delta E into delta E plus Cl alpha dot into alpha dot plus Cl Q into Q. Here if you see that this alpha, this, all are non-dimensional, but if you see here this alpha dot and Q, they are dimensional. So if you want to make this alpha dot from dimensional to non-dimensional, we have to do some multiplication, alpha dot into C by 2U, C bar. So if you see here, if you take this alpha dot, the unit of this thing is radian per second. So it is a dimensional one. So we will see here what is the unit of this alpha dot. This alpha dot is here radian per second into meter. Chord is meter divided by 2 into meter per second. So if you see here, radian into meter into second divided by second into meter. So this meter, this second, this second. So you got here radian. So if you want to make this alpha dot from dimensional to non-dimensional, we have to multiply it by C bar by 2U. So it will become the non-dimensional. Same way, if you see here, Q is also in radian per second. So in this also, the same type we have added here Q C by 2. So here radian per second into meter divided by 2 into meter per second. Okay, so we have seen here that these things are happening. So now if we talk about Q. So Q, so what is the Q? It is this is the aircraft axis. This is the center of gravity. And if I put a tail here, aircraft is going with velocity v. So the relative velocity, or it is v here. And if you give a pitch rate q, here is the aerodynamic center AC of the tail. So what will happen? If it is going upward, this tail will go down and there will be a relative wind in this direction. Assume this is the small v. So what will be this? And from here to here, AC to CG, the distance is LT. This is the velocity v. So we know that the rotation or angular velocity here, this will be what? This will be Q into LT. This velocity will be how much? This v will be Q into LT. So it is omega r. This v is equal to, we know that v is equal to omega into r. So r is here LT and omega is Q. So we got a small v here, QLT. Now this upward, so this is the relative wind v, and this is the your QLT. So what is this angle? This is called delta alpha, and this is due to the tail. Due to the pitching motion, we got the additional angle of attack, and this additional angle of attack tan delta alpha t is equal to QLT by V. So for a small angle, we can make delta alpha t is equal to QLT by V. So this much angle of attack has increased at the tail. So it will increase, develop a delta L, and this delta L will generate a moment opposite. It is minus CM T. It is generated. So here the time factor is involved. Here this Q is per second. This Q per second means here the dynamic conditions are existing. So I can show here by this aircraft. If this aircraft is flying and you give positive pitching Q upward, this will go down by going this, a relative wind will hit here. This relative wind, which is shown here, is small v. This small v is this pitching q into from here aerodynamic center to this center of gravity. This is LT. So this q into LT, this much velocity the wing will experience, this horizontal tail will experience that much velocity. So it is to be ensured that the velocity is achieved in this way. And this hitting of the velocity from the bottom will generate a force upward direction, and this force into this direction will this distance will generate a pitching moment down, and aircraft will be pitched down. So the purpose of horizontal tail is to give longitudinal static stability. But here we are talking about dynamic stability. So it is a per unit time how much it is coming down. That is the part of our dynamic stability. So, and these are very much required for equations of motions. Now, I will discuss about few questions, and in this we will see that how these things are working. So, the first question, what is system of reference frames? You know that in aircraft, the pilot is flying or the passengers are with the aircraft and they are following some different reference systems. Person who is sitting on the ground and monitoring and controlling the aircraft, they are called the air traffic controller. They are sitting on the earth, and the person engineer who is operating or making, designing, fabricating, doing analysis, he is in the lab. He or she is in the lab. So how these all three peoples have to be related? So that is the issue. And in olden days, due to the lack of high-speed computing, computers were not there. Lot of accidents have happened because this was not able to calculate properly the acceleration, the velocity, the distance, the location, the navigation guidance was not so accurate. And nowadays we are able to get this type of accuracy by the help of existing technology. So here, what is system of reference frames? A frame of reference is a set of coordinates that can be used to determine position and velocities of object in that frame. Different frames of reference moves relative to one another. So here a very simple examples are given, that a person is in the train and he is sitting in the train, and one person is outside of the train and he is in platform. So the person, he is lifting a ball from his hand and it will go and it will come down to his hand only. Okay, here. But the one person who is outside in the platform, he will not see that it is coming like this. He will feel that it is flying like this. It is moving in a parabolic path as shown in this second diagram. So that is the feeling of, it is a reference feeling, because the person who is inside the train, he is in body axis, and the person who is on the ground, he is in Earth's axis system. So both are having the different axis system. So the person who is on Earth, he will feel different thing, and the person who is inside, he or she will feel a different issues. So we have to ascertain that aircraft is flying and pilot is the main person. We should try to make that what the pilot is feeling, what is the aircraft is experiencing, the velocity and all other parameters, same thing the ATC person should also experience. That is why nowadays the transformation of one axis systems to another system is done by the help of the onboard computers, and these computers will try to make the very accurate measurement of different positions, velocity and other parameters. The different observations occur because the two observers are at different frame of reference. So I told you that the 2 here, 1 and 2, both are, and they are in the different frame of reference. So their observations will be different. Basically, we have the 2 frame of reference. One is a classical and another is inertial. So we know that the Newton's laws are only applicable for the inertial frame of reference. So all the derivations which we make by the help of the mechanics or the fluid dynamics or in this aircraft stability and control, they are derived with the help of the Newton's laws, and these laws are applicable only for the inertial frame of reference. So we should be very much careful about application of these equations when we are using in aircraft. Here this we can see the difference of frames of references in 1D. We can see here that this is the one system. Here S is the laboratory. So here this you can see here, this is the laboratory. Here you are here, this is the lab, and one A is moving in this direction, B is also moving. So this person who is here, he will feel the different thing what this AB is, because both are moving in the same direction. So a relative velocity he will observe from here. In another case, if you see that if you are sitting at the A, that is the S1 frame. So this is the reference frame here, and if this is moving in this direction and this is moving in this direction. So if you are sitting here and it is going like this and it is coming like this, he will feel like this. But if you are here at B, so you will feel that both are coming towards you. But if you are here, you will see that one is coming to this direction, another is going away. And if you are here, both are going away. So you see that everywhere, one laboratory is there, one A is there, one B is there. Here also the same, but where you are sitting, if you are at here, you can see this is the earth. Here you can see a body, another you can see another body. So if you are sitting in this A, you will feel that this is moving in this direction and this is moving in this direction. If you are at the B, you will feel that both are coming towards you. So 1D motion of A and B in the reference frame of B. So it is a reference frame of B, this is the reference frame of A, and this is the reference frame of the laboratory. So I have told you just now that we have the pilot, we have the ATC, and we have the engineer who are making. So all these three will have different issues to tackle that we have to take care of. Now, next question. What is inertial reference frame? We know that inertial reference frame is one in which Newton's first law of motion is valid. In inertial frame of reference is one in which the motion of a particle not subjected to forces is in a straight line at constant speed. Hence, with respect to an inertial frame, an object or body accelerate only when a physical force is applied. So, you can see the Newton's first law. If any particle is in state of motion, it will remain in the state of motion. If it is in the rest, it will remain in the rest till the time some external force is not applied. Same thing here, and this law is applicable for the inertial reference frame. That I am going to discuss in detail about inertial frame. So, how many axis system exist? We know that we have the body axis system fixed to the body. Then we have the earth axis system fixed to the earth, assumed to be inertial. Stability axis system with respect to the relative wind. So we normally in our aircraft stability and control, we study about these three axis system: fixed to the body, fixed to the earth, and fixed to the stability axis. And these all three have some very important results for different references. We have to understand this thing very much carefully. Now I am talking about the body axis system. This I am showing you here. This is the aircraft. Aircraft is flying. If we assume that the center of gravity of the aircraft is here, pilot sitting on the aircraft center of gravity, towards the nose, if you see here, towards the nose, in this direction, it is a positive x. Towards the right wing, from here to here, towards the right side of the pilot, you will have the positive y, and towards the earth, this is the positive z. So we have to understand that body axis system is fixed to the aircraft, with its origin at the aircraft's center of gravity. X-axis out from the nose, I have just now explained. Y-axis out from the right wing, and Z-axis down through the bottom of the aircraft. Pilot sits in this axis system, easy to find forces and moments. Okay, so it is easy for the pilots. What he experiences, same thing aircraft behaves. So this is the body axis system, and we know that aircraft, the equations of motions are derived with the Newton's law, and just now I have told you that Newton's law, these equations of motions, Newton's law are only applicable in the inertial frame of reference. But the real aircraft is experiencing so this real aircraft is facing body axis system. So we have to convert the derivation, which equations or formulations which we have received with the help of this transformation from one axis to another axis system. Now we have the next question, and in this it is what is the stability axis system? So this we can see in this diagram. This is the body axis. This is the positive x. This is the positive y, yb, xb, and zb. And the direction of the flow is in this direction. This is the relative velocity of the aircraft, and it is in this direction, and it is shown by the v. If we tilt from here to here, if we rotate from this position and match with the direction of the flow, then this system is called the stability axis system, and this is very useful for the wind tunnel testing, experimentation on the wind tunnel. So in this, what happens? This force will be here, so lift force will be perpendicular to this, drag force will be parallel to this. So both forces we can calculate very easy without any problem. So if you tilt from here to here, Z will be from here to here. But in this y-axis, YB will be YS. So YB will be YS, means the lateral axis YB and of the body axis system and the lateral axis of the stability axis system both are coinciding after motion of this aircraft also. So the stability axis system is rotated relative to the body axis system through the angle of attack. X-axis points in the direction of the projection of the relative wind. Okay, in this, just I have shown you, it is going like this, and this is the relative wind. Origin of the stability axis system is at the aircraft center of gravity. Origin is both, and y is also common. Y-axis is out, the right wings same as a body axis system. The Z-axis is orthogonal to the point downwards perpendicular to the x-axis, useful to define aerodynamic forces of lift and drag. I have shown here, this L is a lift and D is a drag force, and you can see that if you define from here, the angle of attack alpha will be used. Okay, it will be like this. So this alpha, but if you are making a stability axis, this alpha will be vanished. So L you will get directly the value which your measurements are obtained. They are the direct value which you get in strain gauges. This will be very useful for the aircraft. Now What is earth axis, earth fixed axis system? So far we have discussed about the body axis. Second one is stability axis, and we have seen that body axis system is useful for the pilot because the pilot is observing the real parameters of displacement, velocity, accelerations, all motions, rotations, pitching, yawing, rolling, all is experienced by the pilot, and these all are rotated with respect to the center of gravity. In body axis system, we have seen that X is towards the nose, Y is towards the right wing, and Z is towards the down, as shown in this diagram. Okay, this O is the center of gravity. But Earth is here, frame of reference of the Earth. So here, this XE is north, facing north. Y is facing east of the Earth. And this is the center of the Earth. Center of the Earth. So, when we talk about the Earth axis system relates with reference to the Earth. And we take Earth as an inertial frame of reference because we assume that Earth is do not have the change in the acceleration. It moves with a constant acceleration, and the speed of the motion of the Earth with respect to the speed of the aircraft is very, very slow. So, we assume that Earth axis system is also inertial axis or inertial frame. Inertial frame. Okay, so these are the systems, and we have to understand this Earth axis system. Now, what are the force vectors which are used in our aircraft equations of motions? I am talking about few of them which are very much used. So the first one is weight vector W of the aircraft is conveniently represented in the Earth axis system. If you represent the weight in Earth axis system, it is very, very convenient to use. So here F gravity Earth is equal to F GE 00 W Earth, and this W is equal to mg. So here 0 0 mg. It means 0 is x. So in x direction it is 0. In y direction 0. Only in z direction it is a mg. So this indicates that if the aircraft here, this is the aircraft, and if this aircraft, it is a W, and this W always acts towards the Earth. So it is very much, any case, it will Earth, W will attract towards the center of the Earth. So here the matrix will be 0, 0 and W. Means there is no X component, no Y component and no Z component for the weight vector W, and it is very much easy to in Earth axis system, Earth, as shown in this matrix. Okay, so it is very much easy. But once we talk about the aerodynamic forces, these aerodynamic forces will not be very much convenient if we use the Earth axis system or the body axis system. So the aerodynamic forces are conveniently displayed in the stability axis system, where drag D acts in the negative x direction and the lift L act in the negative z axis. So F aero is equal to Fa is equal to minus D Fay minus L stability. Here you see minus D. So if I make the aircraft like this, this is the center of gravity. So this is the plus x. So if you want to, minus x means what? It is in this direction. So D is in this direction, drag. D is equal to drag. So drag will act in this direction. But what about the lift? This is the positive Z. But here it is a minus. So it will act opposite to this. So this is the lift. So this lift and drag, they are opposite in nature from the x direction, the opposite is drag, and from the z direction, opposite is lift. And Fay will remain the same. Means the side forces will not act as Yb is equal to Ys in a stability axis system. So in this system, if you see, Xb is equal to, will be matching towards the relative wind. It is Xs, and here also it will turn. This is the Zs, this is Zb. Okay, so like this it will be changing. So it is very much easy to represent the aerodynamic forces or the aerodynamic vector forces in this format. F arrow is equal to Fa minus D, it is in x direction. Fay, it is side force in y direction, it is positive, and minus L, and these are represented in stability axis system. It gives a very good concept if we represent these aerodynamic forces in stability axis system. Now the third force is thrust force, and this thrust vector can easily be expressed in the body axis. Okay, so thrust force, if you represent in a body axis, so if you see here, if I represent in the body axis here, so if this from center of this thing is phi, so we can write that t cos phi in x direction. Okay, so just I will write here, so it will be easy to explain. If this is the aircraft, this is the x, this is the y, and this is the z. And if your aircraft is, your engine is fixed here, the propeller, and this is the phi. So in x direction, you will have t cos phi t, just t cos phi t in x direction. In y direction is 0, this is the y, is thrust is equal to 0. And in z direction, this will be opposite. So here in this direction, it will act minus t sin phi t. So this is in a body axis system. So thrust force, the thrust vectors, if you represent in body axis, it gives the correct value. So t cos phi t 0 minus t sin phi t. So here phi t is the angle between the x body axis and the thrust vector t as shown here. This is the phi t here. This is the angle phi t. This is from here to here. So like this, we can show the force vectors of weight vector, aerodynamic forces, and the thrust vector in different scenarios. Now, earth axis to body axis transformation. Just I have explained you that there are different peoples who are operating, maintaining, designing the aircraft. The pilot is operating, and he is the person who should know the exact value what the aircraft is behaving. However, the person who is sitting on the in the ATC, he is also very important, because he is not controlling only one aircraft, he is controlling a number of aircraft in its range. But what happened? The ATC is in earth axis system, pilot is in body axis system, and I have told you that it is very convenient to express the aerodynamic forces in stability axis. So the designer is testing in a stability axis system. So how these all three people will be matching their ideas? How they will give the same aspect as they wanted? So here you can see that transforming a vector from the earth axis system to the body axis system requires 3 consecutive rotation about the z-axis, y-axis, and the x-axis respectively. So it is a systematic approach we have to do. First we have to rotate about the z-axis, then y-axis, and then x-axis. And in this, Euler's angles are very important. Euler's angles are used to rotate the vehicle carried earth axis system into coincidence with the body axis system. And the Euler's angles are represented as yaw, psi, pitch theta and roll phi. So this should go in the proper rotation. First yaw means z axis, then pitch axis, and then the roll axis. Euler's angles are very useful in describing the orientation of the aircraft with respect to the inertial space. So just I want to express here what is the meaning of z rotation, y axis rotation, and x axis rotation. You know that this is the x axis from here to here. This is the y axis in this direction, and this is the vertical. It is a z axis from here to here. So if I want to convert from earth axis system to the body axis system, what I have to do? So first it is flying on the earth. Then first I have to do psi, means about z axis. Vertical axis means I have to make positive yaw. This is the right side. If your nose is going right side, it is a positive yaw. So it has to go like this. So first rotation is psi. Then next rotation is like this. Then with respect to y, it is a pitch. Then you have to rotate positive upward, theta. Then we have to go for roll. Positive roll means right wing down. So in this condition, you make phi, roll. This is the angle from the horizontal to the center of this center line of the wing. This is called the phi. So this right wing has to go down. Then it is a positive. So if you want to convert from one reference, earth reference, to the body reference, first we have to rotate towards the right. That is the first case. That is the yaw, phi, psi rotation. Then theta upward, nose upward. This is the pitch rotation or theta. And then right wing down, roll. This is the phi rotation. This process, if we go one by one, we can reach to the required from one axis to the another. If you want to convert from body axis to the earth, then you have to go in reverse order. First you have to roll, then you have to pitch, or then you have to yaw. So you can go from earth to body or body to earth. And same way, you can go from body to stability and from stability to the body axis system that we will be seeing here. Now, what is the proper order of Euler angles? This is also very important. Just now I have discussed. You can see here this diagram. If you want to go from earth axis system to the body axis, first you have to rotate psi. Okay, it means in a z axis. So if I make x axis, y axis, and this is the z axis. So what I have to do? This has to move upward in this direction. This is the psi. So in this will also move in this direction. But so now this initially is ye, and here is this is xe. This is the ye. So it is now ye prime. This is the xe prime. This is the one rotation. Now we have to rotate pitch theta, means new case this ye1, ye prime will be constant, and this will move towards upward. So this will move theta. So now this is constant. So with respect to this, it will move towards the theta. So this z, if you z will be here, this is zb. So now this will be z. This is new case, and this is the new case, and this is the theta. So now this is the theta. This is the prime, double prime, and here is x double prime. I will not write e here, x double prime. So I have theta. Now I want to make further rotation with respect to this x double prime. So x double prime will be constant, ye and ze, this will change. So here you will make a rotation about phi, and here also you will make a rotation phi. So this will be the z triple, and this is the y triple prime. So in this way, you will get from earth axis to the body axis system. I think it is clear. I have already, so yaw angle psi. So we have three angles, yaw angle, pitch angle and the roll angle. Yaw angle psi is defined as the angle between the projection of the x body axis onto the horizontal plane and the x axis of the earth axis system. With the earth x axis defined as north, the yaw angle is the same as the vehicle heading angle. So this yaw angle and the vehicle heading angle both are the same. Next is the pitch angle. Theta is the angle measured in a vertical plane. So if I want to show here, so this is the vertical, and if in vertical plane, this is the y and this is the z. So if your nose is going upward like this, it is a pitch, and yawing with respect to this. So this is the yaw angle and psi, and this is the pitch angle, and this is the rolling this side towards the right down. It is a positive phi. Okay, so the pitch angle theta is angle measured in a vertical plane between the x body axis and the horizontal plane. The roll angle phi is the angle measured in the yz plane of the vehicle body axis between the y body axis and the horizontal plane. So these are the three Euler's angle: yaw angle psi, the pitch angle phi, and the roll angle phi. How much is the range of the Euler's angle? We know that the first angle is psi and this is the yaw angle. So how much your aircraft can go in yaw angle? So it can go from 0 to 360. So if you start from here, this is thing, and you want to go from here, you can go any direction. Up to 360 you can move. You can reach here. So this is called from 0 to 360 you can rotate in a z axis. This is the z. So at the z axis your aircraft can move from here. Just I want to show the meaning of this. This is the z axis. It is moving like this. Your aircraft can move all the way, in a circle with respect to the z axis. So this is the range of your yaw angle or Euler's yaw angle psi. What is how much the pitch angle you can do? It is a minus 90 degree to plus 90 degree. So your aircraft is flying like this, nose down, it is a minus, up to it can go 90 degree. This is a minus. And if you want to go plus, up to this 90. So minus 90 to plus 90, your theta can be changed. Pitch angle, the range of the theta is minus 90 to plus 90 degree of pitching angle. How much rolling you can do? Rolling you can do minus 180 to plus 180. So here you can go here. This is the plus and opposite side it is a minus. So minus 180 to plus 180. Right side going down is plus and left side is minus. So minus 180 to plus 180 is the range of banking angle of phi for the aircraft. So roll angle. So this is the range which our aircraft can operate by the given conditions. Okay, so I have covered these 10 questions and hope these questions will be quite useful for the basic knowledge of this module. However, we will be discussing in our next this thing about the perturbation of equations of motion, and in that we will be handling different derivatives of the aircraft, and we can see that these derivatives are very useful. And once we talk about the effect of this tail, and we have seen that how this thing, just I want to show here, if this is your tail, how this tail will, this is the CG. If you give the pitching like this Q, what will happen? This will go up, your tail will go down. This down going tail will generate a relative wind this direction. Due to the speed the aircraft is moving in this direction, the relative wind is in this direction. So the net, this angle of this will change now to this. This is the alpha, delta alpha. This delta alpha will generate additional lift here, and this is called the delta lift. And this, if the distance from here to here is LT, a moment of delta L into LT Cm, and this is a minus, will be generated in this direction, and this will counter this, and aircraft will be stable. However, here if you see that Q is a time factor here, it is a rate of pitch rate. So here the time factor is involved. Time factor is involved, and that is why Q is studied in equations of motion and very important parameters. Okay, so that we have to see that it is understood. And same way, another parameter is alpha dot. So what is the alpha dot? Alpha dot is a angle of attack rate. So if I take this aircraft, and if all of a sudden some gust came, aircraft will start like this, like this, like this. So pitching and rate of angle of attack both will change at a time. If you give the Q, angle of attack will also change. So Q and alpha dot both are related, and that is why we have told in the initial that CL is a function of alpha, alpha dot, Q and delta E. And these two parameters are the dynamic parameters. That we have to be very much clear, that dynamic parameters has to be understood very well. Then only we can find the real equations of motions, and we will be understanding the 6 equations of motions. So we have the equations of motion, and we have the 6 degree of freedom. In this 6 degree of freedom, we have the Fx force, Fy force, and Fz force, and 3 moment: rolling, pitching, and yawing. These 3 forces, and these are the moments. And we will be discussing about these equations of motion. We know that F vector is equal to m a vector, and this m is dv by dt. So by this we will be able, and this m ui plus vi vj plus wk unit vector and divided by dt. So d of dt. So these different directions we have to see for the velocity. Same way we will be finding out the fx, fy, fz, and this is the moment, and this, you know, this moment is equal to d by dt of h. Okay, so this is angular momentum. So what is the angular momentum? The angular momentum is angular momentum h. So it is a moment of momentum or linear momentum. Moment of linear momentum. Okay, so if you see here, this is the, and your mass m is rotating with velocity v. So the, how much is the moment? Momentum is equal to mv. So if we talk about how much is the angular momentum, it is this is the r, so it is the r vector cross mv vector. So this is the h. So these things we have to understand very well, and these parameters will be discussed in our next class. In our next module, this class, we will be trying to discuss about perturbation theory of the aircraft, and I have taken this. These are my references: the Robert C. Nelson, Aircraft Stability and Automatic Control, NPTEL lectures of aircraft stability and control by Professor A.K. Ghosh, IIT Kanpur, and this is my link. And thank you very much for joining the class. It's my pleasure that you are here, and do watch my next video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.